We're here today to talk a little bit about science. I appreciate your interest in this and your upcoming efforts to help make change as we move forward on this. So this is a show of hands. How many of you are science people? All right, so I may have a task for you here. Okay, how many of you are administrators of some sort? Good. How many of you are teachers? Good. How many of you are from other organizations like higher education, museums, others? Okay, just a couple. All right, good. All right, so what we wanted to do today is two things, really. One is I want to tell you a little bit about why we at the department and as a state think that science is critical for success after K-12 for all our students, and how the draft revised standards try to support that vision a little bit. So to begin, I have a task for you. Many of you may have seen this, but it's a very different task when I do it with people who are not science, so this will be fun to do with science people. But I have a little task for you. So imagine for a moment that you're handed a maple seed. Put that in your hand. Imagine you plant that tree and it grows. Plant that seed and it grows into a tree, sorry. And then I hand you a piece of that tree. All right, and I give you a chunk of the maple tree that you have to have two hands to hold. All right, it's a pretty hefty piece of the tree. Where does that stuff come from? Take a moment and write down individually. Where does that stuff, from the seed to that chunk of tree, where does that come from? All right, did you include water? Majority of you. Did you include soil? Did you include minerals? Or nutrients? You can say nutrients as well. Nutrients. I didn't put that one up here. Did you say air? Did you say carbon dioxide? Okay. How many of you have seen these videos, either a private universe or a mind of your own? Quite a few of you. They're amazing videos. They're almost 20 years old now, believe it or not, but they get at this notion of student misconceptions. And many students, right through elementary through graduate school, cannot identify where the mass of the tree came from. You ask them and you get typically the first three: water, soil, minerals, and nutrients. But actually very little of the mass comes from those three things. Most of the mass comes from carbon dioxide in the air. All right, but that's a very, very, very difficult thing to get a grasp of. Right? Because how can you take this stuff that most kids don't even think is something, it's nothing here, or it has no weight, right? That's their perception of it. That's what, if you live in it and not think about it, that's what you think about it. So how can this stuff that I can not see, that doesn't have weight, I think it doesn't have weight, turn into something this heavy that I can barely hold? Right? That's an extremely difficult thing. Those videos do an awesome job. If you haven't seen them yet, go to Annenberg Lerner site, and they start at Harvard graduation. For those of you who haven't seen it, they stop kids in cap and gown and ask them this question, just what I asked you. I took it right from their script, right? And then they pan over to a middle school, one of them in Cambridge and Melrose, just in the area, and they ask middle school kids the same question, and they get the same answer. And they've had instruction on photosynthesis multiple times from middle school to the time they graduate from college, right? And they purposely look at, quote unquote, the good kids, the top kids. And what does it take to change their thinking about that? And it's really tough. But if you don't understand that the mass of the trees come from carbon dioxide, how does that impact your conversation about global warming now? Right? If you don't understand that's what happens to the carbon dioxide in the air, or one of the critical things that happens to carbon dioxide in the air. So that's a key kind of point that we have for why these standards are so important. I'm going to come back to this in a second because I want to show you how we treat photosynthesis in our current standards and how we treat it in the revised standards to follow up on this point. So why is science and engineering important? So first of all, there's these kind of critical issues that we have as a society. Whether or not you're a scientist or artist you've got to deal with these kind of issues in our current conversation. We have these things that are confronting us. If you live anywhere in Massachusetts, you live somewhere close to water, and so we have sea levels rising pretty soon. Even if you're not near water, you're out in Worcester, we have invasive bugs coming in, right? What are some of the issues that we have to think about to deal with that? I'm being a little doomsday-ish here at the moment. All right, but then there's also this part about, what do students do after they leave high school? What are their opportunities? This is data that comes from a colleague at the Department of Higher Education. She tracks job data. And first of all, she's finding in discussions with them and with businesses, majority of job openings in Massachusetts that require a college degree require strong STEM skills. Right? So even if you're not in a STEM field, there is a baseline expectation. Right? We've already made this argument for mathematics and literacy. We're seeing the same thing with science, technology, engineering. There's a certain amount of literacy you need to be in almost any job now. But almost more impressively, she tracks job postings here in Massachusetts. And for the period of 120 days ending in late September, of all the jobs posted, 32% were STEM jobs here in Massachusetts. 46% of those with a median pay of $40,000 or above were STEM jobs, and 60% that paid $60,000 or more were STEM jobs. Right, so if you want to talk about opportunities for students, STEM is a critical consideration. And we're not just talking about mathematics, we're talking about science, technology, engineering. So as we think about college and career readiness, and you already know the conversation we've had there in college and career readiness and math and ELA, we've had the same kind of conversations in science and technology engineering where we bring higher ed, businesses, others together. What comes across as being critical to success after a student leaves our K-12 system has to do with the type of skills they bring and thinking practices they bring. You need science content to do these practices, but it's really more about your ability to reason scientifically and technically, to engage in the kind of skills that science and engineering prepare students for. You can't do that separate from content. But nowhere did we find somebody who said, yeah, you need a high school biology course or you're not going to be successful. Nobody said that. But everybody said you need these skills and practices. What are those? These are the 8 practices that are in the NRC document and NGSS and in our state version of the standards. There's not much new here. A lot of you have been working on scientific inquiry or engineering design, recognize most of these. They're repackaged a little bit or reframed a little bit. And there are some different emphases than we've had in the past. You'll also notice that it's science and engineering together. Right? The practices, the skills that a scientist uses and an engineer uses are very similar with the exception of purpose and product, number 1 and number 6. There's differences in purpose and product between the 2 disciplines. You also notice some connections with ELA, literacy, and mathematics. So you see a lot about modeling, which if you know the math standards, modeling is a big part there, as well as computational thinking. And then literacy, if you look at the last 3, you'll see a lot of connections within the literacy standards, particularly around argument with evidence and informational text. In the standard, in the revised standards, content and these practices are integrated together. And we think there's a couple important reasons for integrating them. This document, America's Lab Report, is a good reference if you want to take a look at some of this. It's getting a little dated now, but it's still kind of a relevant piece. But if you look at students doing science along with learning science content, science knowledge, the kind of outcomes we get are the kind of outcomes we want as a state here. Better understanding of science content. They're just not memorizing it for the fact of memorizing it, but they actually get to see it in action and do it in action. They actually achieve a more sophisticated understanding of the concepts partly because they're doing it in authentic context, and it increases their interest in pursuing STEM in further courses for the degrees for their careers. So what does the standard look like now? I've color-coded the first part of it, which is a practice. References a particular practice, in this case, modeling. And the content is in blue. In this case, it has to do with phase change. I'm not going to read it to you, but you can see how those get merged together. Our current standards have verbs, but they're generic cognitive verbs. Explain, illustrate, compare and contrast, the kind of Bloom's taxonomy verbs. So they're basically content only. The standards in the revised version will be integrated practice and content just like this. You'll see a couple other structures there: clarification statement, assessment boundaries. A clarification statement replaces the IEs, EGs that we have kind of in the middle of our sentences now. Most importantly here, these are not activities. Standards are an articulation of what we want students to learn as a result of our instruction. They're the outcomes, the desired outcomes. Standards do not define how you teach. The trade-off with taking this method is sometimes these read like how to teach. They read like activities sometimes. But that's not their intent, and that's something that we have to figure out how to message and illustrate. So it articulates the desired student performance, and it does not limit your curriculum instruction. So for example, if you're teaching phase change, yes, modeling is a good way to teach phase change, but so is collecting and analyzing data, doing an investigation, looking up information somewhere else about it. All those things are all good to do in a curriculum instruction. This is just the desired outcome. The core ideas, the content, if you will, the standards are organized by core ideas that progress across time. And so take, for example, our tree that we were just talking about. Core ideas here having to do with, the fact that gas can exert pressure, gas has mass, that leads to that mass in the tree, that mass goes somewhere, that mass contributes to, that process contributes to discussions about global warming. Those are all related ideas that get more sophisticated over time. We want those students to be able to explain natural phenomena in their world, as well as design systems. That's where the technology engineering part comes in. Right, so if they can't do that, if they can't take that chunk of tree and say, where'd that mass come from, then they're handicapped in engaging in discussions about global warming later. Okay, and that's just one example of any number that you can choose from. So take a look for a moment. We're not going to read these out loud. This is our current standards and how we talk about photosynthesis, which is the heart of that tree example. So we teach photosynthesis currently, assuming you're teaching it at all the grades here. We're teaching photosynthesis at elementary, middle, and high school. We tend to put an energy focus on it, which is important. And by the way, energy focus is still in the current standards. But you can't really find a place here where they talk about the mass. How does the result of photosynthesis result in plant matter, in that mass that you're holding? Right? So if you're teaching these standards, our students, just like in the videos from 15 or 20 years ago, are not able to make this connection between an important process like photosynthesis and what's happening to the mass in that tree. And you'll notice we not only put an energy focus on it, we also put a focus on kind of the formula, if you will. Right, at middle school, we're basically teaching the formula at middle school. Okay, but what's that formula represent? That's the critical part. Okay, and it's not until you get down to high school and it says the reactants, products, and basic purposes, right? So what are the products? Right, if you just look at the formula, you would never convert that product to parts of a tree or parts of a plant. So what's it look like in the revised standards? And I've only pulled those that relate to matter or mass here. Right, so there's still some standards about photosynthesis and energy, which I haven't included here. Again, we reference it elementary, middle, and high school, you'll see that you don't actually get to the formula until high school at this point. All right, so we're trying to de-emphasize that formula and emphasize what is the core idea. What's the point of this process, not what is the process itself. So you'll see at grade 5, plants get materials they need, using air, water, and energy, to produce sugars and plant materials. So it's not a big change, but you now get explicit plant material. At middle school, you're now talking about that matter, cycling of matter, not just cycling of energy, but cycling of matter. And then at high school, now you get down into what is that formula, and the products now being extended to sugars and carbohydrates, which are the foundations of plant materials. So I hope you can kind of see that transition in this one example. Right, for a long time, we have taught mathematics and science, you know, about what are the kind of representations of processes. Formulas are a representation of something in the natural world, and we're trying to emphasize that's important, but more important is, do they understand the concepts that underlie those representations? Can they use those in productive ways? This is a little bit washed out. I probably need to do a different version of this, but we're trying to represent those progressions of learning across time using a visual of the standards. So some of you have seen these before, but these are what we're calling strand maps. They're based on, if you ever use the AAAS atlases of science literacy, they're based on that. The basic idea here is that the standards themselves are in each of those cells. The cells are color-coded by core ideas, so you're looking at a physical science map here. Those dark purple all have to do with force and motion. And the columns are the different grade spans, pre-K starting on the left, going over to grade 5 on the right. This extends up to middle and high school as well. But the notion here is that what you can't really see as well, you can just get a hint of, is there are arrows between some of those standards. And so that's what the strand map adds, is those connectors between standards. And those connectors are meant to illustrate how the concepts progress over time. So if you think about it from an instructional perspective, if I'm at grade 5 and I'm going to teach the standard that's up in the upper right-hand corner, don't try to read that. There's an arrow, which you can't really see that well. There's an arrow that comes from the grade 2 standard at the top, about in the middle at the top. There's an arrow from that grade 2 standard over to the grade 5. What that says instructionally is students really need to know that grade 2 concept pretty well to be successful in the grade 5 concept. And so I should check that to be sure that students are ready for it. Okay? So just like the tree example, if I'm thinking about photosynthesis, and I'm thinking about where that mass comes from, well, I can't, even if I understand what the products of photosynthesis are, if I don't understand that gases matter and has weight, photosynthesis isn't going to make sense to me, conceptually. Right? So while we may have a standard about photosynthesis in middle school, there's additional standards about gases and the properties of gases down here in elementary school, which are critical to understanding that concept about where mass of a tree comes from. And correspondingly, when you get to high school and think about global warming issues, if you don't understand what the role of trees are in that carbon cycle, then you're going to be hampered in thinking about global warming. So those are a couple of the big picture changes, why we're changing the standards to some extent. Clearly we have a responsibility to update standards periodically because science changes. Think about what's happening in terms of genetics over the past 10, 15 years, right? The standards should reflect some of that. What's been happening in earth sciences over the past 10 or 15 years. A lot more thinking about earth systems than we used to have, which are now reflected in the revised standards. So that's kind of conceptually and the underlying goals. We have done some additional things with the standards that I want to make you aware of that have more to do with kind of implementation and policy. So one of those is to present the standards as grade-specific standards, not grade span standards for pre-K to 8. All right, previously we've had grade span, pre-K 2, 3, 5, 6, 8, and it was up to districts to figure out where exactly to put those. We're now presenting the standards grade by grade. And we think this is important for a couple of reasons. One of which, collaboration and sharing across districts about curriculum, about resources. And for pre-K to 5, we've tried to keep as much aligned with next generation science standards as possible. All right, so even nationally, you should be able to find resources that have been developed elsewhere and make use of them. Student transience was a big issue for many districts. Right? So even within district or across a small set of districts, if students started moving building to building or district to district, and one grade 6 was set up, as a life science focus in one school or district, and grade 6 with earth science in another one, that could throw off a student's opportunity to learn by quite a bit. So this is another way to help with that transience issue. And then third, we were able to write standards specific to a student in a particular grade, right? Rather than write them for the end of 5th grade and you're trying to teach them in 3rd grade, or the end of 8th grade and you're trying to teach them in 6th grade. Now, with that said, there's nothing that I can hold you to those. All right, so we're presenting them as grade by grade standards for these, we think, important reasons. But the reality is it's still up to districts to determine whether or not they want to follow that. All right, and I'm going to talk about MCAS in a little bit, but fundamentally we don't anticipate MCAS going grade by grade. Right, so there's still nothing there. So we're encouraging people to follow them for the kind of reasons we have here. We're also taking the opportunity to integrate disciplines, so life science, physical science, earth science, and technology engineering within each grade. Whether or not that leads to integrated curriculum is really up to you and curriculum developers, but that's the intent there. But it's still, even though we're presenting in this way, it's still up to individual districts. At the high school level, it's a different story. The high school level, we're not going to change that structure at all. We're going to maintain our current structure, which is quote-unquote introductory 9th or 10th grade levels standards for those courses. That's our current model. We have no, going back to that career and college readiness, we have no evidence and no rationale for requiring you all to take a biology course or have students take a biology course or a chemistry course. So every district determines what your sequence is for high school courses, and we have no reason to tell you otherwise. All right, so some of you are doing physics first, some of you are doing biology first, some of you give your students options. All that's good and all dependent on your decision making. We want to maintain that because we have no reason to force you to do otherwise. We have been able to achieve an overall reduction in the high school standards for those introductory courses. And keep in mind, these standards do not address upper level electives at all. Right? So they basically are just the quote-unquote introductory 5 courses. We are going to do a little more work on the practices, going back to that career and college readiness notion. Practices were critical. You need a context, a content in order to develop those practices. So the content still matters, but we want to make sure that there's also a progression of these practices, because students engaged in those science and engineering practices at 9th grade probably looks quite different than those students as a 12th grader engaged in those practices. And just to highlight the fact that we have tried to be purposeful about the integration and overlap of some of the practices with literacy and mathematics. So this is a Venn diagram that we've stolen and people seem to respond to well. It's taken from NSTA, originally it was done out of California originally. And you can argue about some of the placement of some of these things, but it highlights kind of the overlap of the disciplines. So the blue is the science and engineering practices that I just showed you. The red are the standards for mathematical practices, if you've looked at those. And the yellow are the anchor standards in the literacy document. And you'll see that they overlap, right? And that was done with purposeful intention, so that students start to see more consistency and commonality across the disciplines. So you'll see in the center there, those are all the ones related to argumentation, arguing with evidence. Now, what counts as evidence in each discipline is different. How you make an argument is slightly different, but the fact that you have a similar structure there to use across disciplines should be a boon. So just taking a look back here for a moment, the changes that we're making in these standards are aiming for the following kind of shifts. One, around relevance. Can students use what they know for purposeful reasons, to explain the world around them? Not just that they know a bunch of stuff and we can test them on it and they can spit it back, but can they apply it? If that's the goal from the standards, what's that mean from instruction? Thinking about explaining phenomena rather than teaching knowledge. If we look at rigor, bringing the practices together with the content is just like in math and ELA, that's one way of enhancing the rigor of what we expect of students. Not just that they're learning more, that's not what we mean by rigor, but that they're actually doing something with it and are held accountable for it. What's that mean for curriculum instruction? It means that doing science is not a once-a-week thing. It's not lab on Thursday anymore. It means it needs to be integrated into our curriculum instruction on a fairly regular basis. It does not mean we need to do full-blown inquiry all the time. All right, so we can talk more about that later. And then coherence. Very purposeful and thoughtful building of ideas across time and across disciplines. So from an instructional perspective, that means that as a fourth grade teacher, it's not just that I go copy my page, my fourth grade page and teach just that, but I have to help students understand how they're in this storyline in their learning. Where are they coming from? Where are they going to? And how does what we're teaching them now contribute to that? Okay, I think I just have a few more moments. Just want to give you a sense of where to find information. If you write nothing else down, and by the way, we should be able to get this PowerPoint to you.
I'm going to send it to everyone who's
Thank you.
signed up.
But if you write nothing else down, that link right there is the link to write down. That's where you'll find the standards, all the resources and whatnot, the strand maps, everything else.
Everyone will get it.
Yep. We have quite a bit there. The standards have been up since December. We are not moving the standards forward for adoption until 2015-16, but they are available, and districts can be, and many are, making the transition or beginning the transition now. Right, but that's up to districts at this point. Districts are doing that in different ways. They're either jumping right in, and by the way, the department, in the FAQ on that page, the department is saying, if you want to, for K-8, don't try to keep the old standards up, go right to the new ones. There's enough content overlap. But some districts are saying, we're not ready to shift our content, but we want to do more with the science and engineering practices. That's an excellent way to start the transition if you want. And since we won't be adopting until 2015-16, MCAS will not change until 2 to 3 years after the adoption. The high school test will take even longer because there's competency determination, impact for student graduation that we have to consider there. So in my 30 minutes, I hope I gave you a bit of an overview. I know we'll have time for Q&A. I think we have the panel coming up next. And I look forward to working with you. It's going to take all of us working together and sharing resources and sharing materials, sharing lessons learned to make this happen. I know the science community has been chomping at the bit to do something. They've been watching ELA and math for a long time, and science is ready to do something. Part of the reason for delaying the adoption was because the school districts weren't quite ready to support you in that. So hopefully school districts are beginning to think about that, and we're going to try to help as much as we can at the state level as well. But this process over the next 3 or so years hopefully will be a collaborative one that we all can help each other with. And I hope that you see what we've done with the standards are meant to support important kind of goals and needs that our students have in the future. So thank you so much.